Let's start. I'm Nikolai, CEO and co-founder at Karoot. And today I'm going to talk about zero instrumentation observability. And we will discuss this from eBPF perspective. Like a little bit notes about me. I am an ops guy initially, and I worked a lot on building reliable infrastructures. And for some point, I started to build observability tools and platforms, and now I'm focused on building Karoot. Karoot is an open source observability tool that covers all the aspects of observability in terms of metrics, logs, traces, and so on. But let's start from the very beginning. What is observability? From my perspective, observability is being able to answer a question about your system. These days, systems are getting more and more complex, and that's why we should be able to find issues and troubleshoot them quickly. We should care a lot about observability because we have to manage systems containing hundreds and even thousands of services. And why do we need that? I want to highlight 3 points here. The first one is availability. We can, if you're doing business and online business, we should make sure that our system is available for users. The second one is the performance of our system, because there are a lot of researchers that prove that response time, for example, or application latency impacts our user satisfaction and our revenue at the end. And the third one is cost. If we can optimize some of our services, allowing them consume less resources, we will spend less budget on cloud. And why I want to talk about zero instrumentation observability. From my perspective, it's super important because before, I'm a relatively old guy, and I worked in this space already when systems were super simple. We had dedicated nodes for our monolith application. They communicate with some databases, and that's it. So troubleshooting in such systems were pretty clear, and you need to check the application itself, its database, underlying nodes, and sometimes network. That's it. Really pretty straightforward. These days, we have much more complex applications. It contains a lot of services. We have distributed databases. We have Kubernetes that makes it pretty dynamic. So we have spot nodes that can appear and disappear. And in this, if we're talking about managing such systems, we should care about observability, because troubleshooting can be pretty tricky there. We should follow all the dependency graph and find the bottlenecks. That's why we should proceed some steps to make our system observable. What does it mean? The first step is collecting telemetry data. Any analysis should work on top of some data. In case of observability, we are talking about metrics, logs, traces, and sometimes profiles. Then we should store this telemetry data in some databases and scale them somehow. And the last step is we should learn how to extract insights from this telemetry data. And from my perspective, this is the most challenging part of all the process. But before we will talk about how to collect telemetry data, let's talk about what we need to collect to be able to answer questions. I wrote down some list, but it's pretty high-level list. We should know about in terms of Kubernetes, think about every application deployment, every service, every component of our system. We should know about each component, like their service level indicators, like request errors, latency. We should understand how components communicate with each other. Like we should be able to build service map. Then we should control resource usage, like CPU, memory, disk. We should understand if there are any issues with CPU or memory or something like that. We should understand the status of our network, because, like, in most cases, applications communicate with each other through network, and sometimes it can be pretty complex topology involving many availability zones and even regions. We should collect application logs. We should understand runtime environment such as JVM or .NET runtime or Golang runtime. We should also understand if we have any issues with placement, like orchestrator-related metrics such as status of our applications, like are there any pending pods and so on. We can collect all this data manually, but we should dedicate a lot of time of our team to instrument all the applications using OpenTelemetry SDK, using various Prometheus exporters and so on. But in some cases, it's not possible, or it's pretty tricky to instrument third-party services or legacy services, because you can change their code. And in this case, we can think about how to gather all this telemetry data without the need to instrument and change our application code. And we have eBPF. Like, few words about what is eBPF. eBPF is a feature of the Linux kernel. It allows you to write small program and run them in kernel space, and ask kernel, okay, I know, please call my application when some new process appears in the operating system, or TCP connection is initiated. And the kernel will call our application, and we will be able to access this kernel function arguments and collect some data and send it to the user space part of our program. And one important note here is that eBPF just allows you to write code and run it. So it doesn't solve any observability or security problem itself. And it's really important to understand. And this is like top level overview of what you can do, what exactly you can implement with eBPF. Using eBPF, you can attach to any Linux kernel function call. For example, there is a function in kernel that initiates TCP connection, and you can attach to it, and you can access to arguments of this function and other context. Also, in some cases, using kprobes is not super stable, because in the kernel code, functions can change, their names can change, code can be refactored, or the arguments of function can change. That's why developers decided to embed some static trace points into kernel code. And for example, you have static trace points with some stable argument set, and you can, for example, trace system calls. System call, it's a call from user space program to kernel, like open a file, for example. And like trace points are more stable interface to deal with kernel. Next, we have uprobes. Uprobes allows you to ask kernel to call your eBPF program when some application level function call. For example, you can attach your program to like SSL write function of OpenSSL, and it like this code is executed in the user space, and it allows you to also access to your eBPF program to be triggered on this call. And there are some mechanisms that allows you to keep some values between your program calls in the kernel space. And also there are some mechanisms that allows you to exchange, like send data from user space to kernel space and back. It's like writing eBPF programs can be challenging and pretty complicated process. And it's like, sometimes it's hard to debug. But the good news are you don't have to write your eBPF program, since we already have a lot of open source tools that can help you to gather telemetry data, for example, Kahoot, without the need to write code. Our agent uses eBPF to gather various telemetry data about containers running on each node. It instruments like all communications between the containers. It measures network latency and do a lot of instrumentation that doesn't require any code changes. And it's open source, it's Prometheus and OpenTelemetry compatible. It can send logs and traces through OpenTelemetry protocol, and also expose metrics in the Prometheus format. And let's talk about low-level details on how our agent uses eBPF. First of all, it requires to be aware about all processes on the node. When some new process started on the machine, we should trigger some code and discovers container metadata, such as, for example, if it's a process is part of Kubernetes pod, we need to understand the exact pod, like namespace, pod name, container name, and so on, and C groups. And there's C groups to be able to gather like resource usage metrics. Also, we should trace process exit to know that this process is no longer exist on the machine. And sometimes we can understand that this process has been terminated by the old killer, and mark the event that is the reason of process termination is out of memory event. And also our agent traces open file events to be able to discover container logs and to identify volumes or partitions that used by the container. Also, agent tracks all TCP communications between container. It tracks outbound TCP connections from every process to any TCP endpoint, and it also calculates the number of TCP transmissions to be able to understand to identify situations where there are some packet loss between two particular containers. Then we want to capture protocol level, application level protocols such as HTTP, PostgreSQL, MySQL, and for doing that, the agent tracks syscalls that are responsible for write and read data from TCP sockets. And it's like we will cover this topic in more details. And our agent, like since eBPF requires any program to be like limited complexity, for example, you cannot proceed some complicated analysis right in the kernel space. And that's why our agent process each request or query in two steps. The first one is super optimized step in the kernel, and we like this data looks like an HTTP call, and the more complicated part is processed in the user space code, where we can extract HTTP headers or payload from the request. And let's take a look how it works from the kernel perspective. When we call some HTTP endpoint from curl command, the first we can see syscall that responsible for sending DNS query, then send message. Here we can see DNS response. Then we will see TCP connection event, and next we will send some data to the file descriptor 5, which is socket or TCP socket to google.com, one of their endpoints, and then we will see a response. So in this case, we can easily understand that, like using some markers, we can easily understand that HTTP communication happens here. And the kernel side, we have pretty like stupid and simple program. It uses some like it tries to detect HTTP communications through like matching most common HTTP methods, and it's like super optimal. It only reads like 16 bytes of the payload, and it's like low overhead call. And then when we see some response, we also can match for some markers and understand this. Okay, we've seen HTTP request, and now we had a response. So, and between these calls, we somehow measured timestamps, captured timestamps, and stored timestamp, and now we can understand latency, status code, and so on. And these days, most of communications happen through TLS encrypted connections. And to deal with that, our agent use uprobes to capture SSL, OpenSSL calls, because if we track only like TCP level communications, we will see only encrypted data, and our agent uses like try to capture data between before it's encrypted and after it's decrypted in case of processing HTTP response. So we cover like OpenSSL code, and also since Golang applications use like native Golang's crypto library, we can also cover it with handling special function calls here. So it's like there are some details about how we can understand that the particular application or process uses OpenSSL library, but I don't think we want to dig into this right now. Let's talk about eBPF performance and guarantees that kernel provides us about performance. Because if we set up our agent, we should be we want to ensure that our eBPF programs will not impact our application performance. It's super important when we deal with production environments. And Linux kernel has validates each eBPF program before it loads it, and your eBPF application should meet some criteria. For example, it must have a finite complexity. This means you cannot use loops or something, and you are pretty limited in what you can implement in the kernel space. And also communication between your kernel side part of your eBPF program and user space part occurs through a ring buffer. So in worst case, if your application cannot read all the data on time, your buffer will be overridden, and you will lose some data. But if you're talking about metrics or traces, it's not a critical thing, because this trade-off works in this way. In worst case, you will lose some data, telemetry data, but you can have some guarantees that your application performance will not be affected by the eBPF program. Now let's talk about what we can see using data captured using eBPF. Here is some screenshot from our demo application. This is a Kubernetes cluster with some of services deployed into it, and they communicate through network. And we just installed our agents. That's it. We didn't do anything with OpenTelemetry instrumentation, and we can see big picture. It covers 100% of infrastructure. It can check all the communications between components. We can see how many requests performed within each component. We can see latency. We can see any errors. And it's really cool to have, because it can be achieved in few minutes after the installation. Then, since we track all connections, we can see them not as an overview, but we can see communications between each particular containers. And we can see, for example, here Prometheus cannot connect to some DB components. And it's really cool, because you can know exactly what's happening in your network. And also our agent measures network latencies. Think about it like ping. But the ping measure latency each few seconds, and that's why you can understand network condition between any particular containers here. Also, with eBPF, we track DNS requests, and we can measure their latency, their errors, and so on. So we can see which DNS requests are made by the particular container. And for example, if you have any issues with DNS servers in your Kubernetes cluster, you can see these issues really quick. Also, the agent uses CBF not only for exposing metrics, but also for capturing traces. It can capture individual spans and send them through OpenTelemetry protocol. So you can work with them in UI and see, for example, outliers. You can detect the particular database queries or HTTP request, or Redis request, anything. You can easily understand the particular queries behind outliers on the chart. But if you're talking about tracing, it's like eBPF implementation has some limitations. For example, we don't have any tracing ID. It should be originated somewhere. And in this case, we use eBPF generated traces as individual spans instead of like full feature distributed traces. There are some projects on the market that try to change your application payload and inject like if our agent acts like an observer and it doesn't change anything. Several products try to, for example, add some HTTP headers to propagate trace ID. Our agent doesn't do that, but instead Corud supports not only BPF-based telemetry, but also tracing data generated by OpenTelemetry SDKs. So it supports both, and that's why if you can't instrument some legacy service, you can use BPF generated data to understand its performance. If you can implement OpenTelemetry, instrument your application with OpenTelemetry, supports it. Also, we use eBPF for continuous profiling. It's super useful when you want to explain some CPU spikes. So eBPF is used like with some frequency. Our agent traces like collects stack traces of each running process on the node, and it can understand the stack, and it can provide us with flame graphs. So you can select any CPU anomaly and explain it precise to the line of code. Also, you can compare like flame graph of some anomaly with flame graph, like for example 5 minutes before anomaly, and see the difference. It's really useful when you want to explain, like if you see some CPU anomaly, you can explain it and see what happened there. And a few words about Corud architecture. We have Corud, the main component, which like UI and also collector. It stores telemetry data. It stores logs, traces, and profiles in ClickHouse and metrics in Prometheus. Also, we provide users with our agents, and you can use Corud as an OpenTelemetry backend for metric or for traces and logs. So finally, I ask you to try Corud because it's open source. It can be installed not only in Kubernetes, but also bare metal servers. For example, if you run your databases on dedicated bare metal servers or VMs, you can install the agent there and connect this agent with your Kubernetes clusters. And also you can instrument AWS managed databases with Corud's agent. Corud has built-in advanced observability for most popular open source databases. And if you want to have single pane of glass, and with Corud and eBPF, you can implement them in few minutes. Just try it, and that's it. If you have any questions.
Yeah, thank you for the session. Okay, so we have a question, so let's start with it. So how does eBPF enhance Kubernetes monitoring compared to traditional methods?
Imagine that you have 200 services in your Kubernetes cluster. With OpenTelemetry, you will need to change and redeploy each service. With eBPF, everything you will need to install the agent, and that's it. You will have all this data without any code changes, deployments, and so on. You don't need to allocate time of your development team to obtain observability.
Okay. So if that answers your question, Journal. Maybe. So let's wait for any other questions. So yeah, we have another one. What tools or frameworks would you recommend for beginners to start learning and experiment with eBPF?
If you want to start developing eBPF programs, the best way to start is the book of Liz Rice from Cilium team. It's like the comprehensive book about eBPF. So I can suggest this way. This as a starting point.
Okay. That can be a thing too for you. Okay, another question. So how does eBPF interact with the Linux kernel?
I hope I covered this topic during my talk, but yeah, you can load your eBPF programs and ask kernel to call them on some events.
Yeah, I hope that answers your question, Joyner. Right. So that was obviously covered. You can just check that out from the recorded video. Okay. So yeah, any other questions, folks? You can ask your questions right now. Also, another thing, as you mentioned, Kubernetes is open source. Is there any way to contribute to it?
Yeah, we are looking for new contributors, and we have everything right on GitHub, like initial contribution guide. We distribute code, using Apache 2 license. It's pretty open license, and if you like code, start us on GitHub. It also helps a lot because of we try to build our community.
Yeah, I think we have another questions. With that, we'll wrap our events. Okay. So how do you see eBPF evolving in the future, and what potential applications do you foresee?
I know that like eBPF is used in the observability space, in security space also, and in space managing network communication. For example, the most well-known eBPF project is Cilium, is a network. I don't know how it's called. Network. It's not a plugin. It's not network itself or Kubernetes, and they implement load balancing, network policy control with eBPF. So, yeah.
Yeah, I think that should be it, right? With that, we can end the session, right? So yeah, thank you so much, Nicola, for your awesome session.
Yeah, thank you for having me.
Yeah, thank you so much. Hope to see you soon. Bye.
Bye.